then f achieves an absolute maximum and absolute minimum value on that interval. And so this was our theorem, the extreme value theorem, but really when we apply that, what that's saying is that if we have a restricted domain, a domain that has a starting and an ending point, and we're including the starting and the ending point and all the x values in between, then we're guaranteed to be successful if we want to find a highest point on the function and a lowest point on the function. And the corollary to this is that on the interval from a to b, f will achieve the absolute maximum and minimum values at either critical numbers, meaning where f prime is equal to 0 or f prime does not exist, or at endpoints. And so in order to find an absolute maximum or an absolute minimum, what we need to do is to look at our function, find the places where the derivative is equal to 0 or where the derivative does not exist, and include those x values along with the endpoints and see where the highest y value is the largest y value and the lowest or smallest y value occurs. So there are a couple of practice problems on this. Are there any questions on the practice problems?
45.
45? You and these trig functions.
Yep.
Okay, so number 45, in section 4.1, we've got f of x is equal to sine of x plus cosine of x, and the interval is the interval from 0 to pi over 3 with square brackets, so that includes the endpoints. And our job is to find the absolute maximum and minimum values of f on the given interval. Okay, so the things that I want to sort of double check, I want to make sure that my function is continuous, and it is. It's the sum of sine and cosine, and both of those are continuous functions. So f of x is continuous. And in fact, f of x is continuous from negative infinity all the way up to positive infinity. But in particular, we only care about the interval from 0 to pi over 3. Okay? And we're given a closed interval. We're including the endpoints. So we have a continuous function on a closed interval. We're going to be successful. Okay, so finding the absolute maximum and minimum values, those can occur at critical numbers. And so we've got to first find the critical numbers for our function. All right, so when we look for our critical numbers, we're looking for f prime of x. So our derivative of sine will be cosine, and derivative of cosine is negative sine. So we have f prime of x is equal to cosine of x minus sine x. Any questions so far? Okay, so then we say, all right, well, we want to know where f prime of x is equal to 0 and where f prime does not exist. Let's talk about does not exist first. And in this case, f prime of x exists everywhere because our function f prime is, let me say that again. Our function f prime is continuous. So again, cosine and sine are both defined and they're just being subtracted. So our derivative exists everywhere. So we don't have to worry about f prime not existing. So the next thing we want to do is look at where f prime of x is equal to 0. So we'll set 0 equal to cosine of x minus sine x. And we'd like to find the x values that make cosine of x minus sine x equal to 0. All right, so the question next is, well, how do we figure that out? And so when I look at this, the first thing that sort of might run through my mind if I think back to my trig class is, okay, I've got an equation that involves trig functions. How do I solve that? And the answer is that, well, can I factor? No, not really. Okay. Can I isolate one of the trig functions? Yes, but then it's equal to the other one. So I'm kind of left with a little bit of a problem here. And so I kind of stare at it a little bit more. And when I look at this, if I move the sign over to the left side, I have sine x equals cosine of x. And so if I look at this a little bit longer, I start to say, okay, for what angles is the sine of x equal to the cosine of x? Yeah, 45 degrees. So 45 degrees is an angle where the sine and the cosine are exactly the same for our two functions. I should say 45 degrees is the angle where sine of 45 and cosine of 45 are the same value. So x equal to 45 degrees will work. Now, there's a bunch of other angles that would also work. For example, I mean, I can move to 45 degrees, so starting from positive x, swing up to 45 degrees. I can add 360 degrees onto that, but that would be outside of our interval. Our interval is angles from 0 to 60 degrees. And so just in the interval from 0 to 60 degrees, there's only one angle where the sine and the cosine are equal, and that's 45 degrees. So our x value is 45 degrees. Now, since we're talking about angles in radians, our interval is in radians, my x value should also be in radians. So x equals pi over 4. All right, any questions about finding that x value?
Just a comment in the book where they divided each side by cosine x and got tangent equal to 1.
Okay, so an alternative way of thinking about this is to say, okay, here's sine x equals cosine x. And so if we divide both sides by cosine of x, then on the right side we have a 1, and on the left side we have tangent x. And so another way you can think of this is, for what angles is tangent of that angle equals 1? So that would be another way to think about it as well. Good. Okay, Andrew, does that help you so far? Okay, cool. So now we've got our critical number. Our critical number is pi over 4. There is no critical number where f prime does not exist. So the list that we need to make is a list of x values that include our only critical number, which is pi over 4, as well as our two endpoints, which are 0 and pi over 3. All right, so we've got to plug these x values into our function, and our original function, f of x, was sine of x plus cosine x. And so to calculate these values, sine of pi over 4 plus cosine of pi over 4, well, sine of pi over 4 is root 2 over 2, cosine of pi over 4 is root 2 over 2. For 0, we've got sine of 0 plus cosine of 0. And sine of 0 is 0. Cosine of 0 is 1. So we have a value of 1. And for pi over 3, our sine of pi over 3 plus cosine of pi over 3. Let's see, so if I don't remember these, I can always draw a triangle. And so for pi over 3, that's 60 degrees. So I have a 30-60 right triangle. And so the sine of 60 degrees is opposite over hypotenuse, so that's root 3 over 2. Cosine of pi over 3 is adjacent over hypotenuse, that's 1/2. And so now I have 3 y values. And last time at the end of class, I said sarcastically that the hardest part about the problem is now up to us to look at the list and figure out which is the largest y value and which one's the smallest, and everybody laughed because they were numbers like 17 and -1. And here, okay, now we need to figure out which of these three is the largest y value. And it's not so obvious when I just look at these. So we can do a couple of things. One is that we can number crunch in the calculator and get some decimal approximations. Some other things that I can do are, in the first one I can simplify a little bit, and we get 2 square roots of 2 over 2. And the 2's cancel, leaving me with root 2. In the last one, I have 1 plus the square root of 3 over 2. And so here I've got square root of 2, that's a number that is bigger than 1. And 1 plus the square root of 3 over 2 is probably also bigger than 1. So this guy here is going to be our minimum. Aaron, what is square root of 2 approximately? 1.4. All right, so approximately 1.4. All right, and Will, what do you get for 1 plus square root of 3 over 2? 1.36. Do I have a second on that number?
Yes.
Okay, great. Okay, so we have three y values. Looking at the decimal approximations now, it's easy to see that our largest value is 1.4. So our absolute maximum is square root of 2 and occurs at x is equal to pi over 4. And our absolute minimum well, in this case, our smallest y value is 1, so our absolute minimum is 1, and occurs at x is equal to 0.
In the book, they write like f of 0 equals 1 is the minimum. Is that okay?
Yeah, that's fine too. So yeah, so that would encompass both of these in the same way. Okay. Andrew, does that answer your question?
Thank you.
You're welcome. So what in your opinion was the biggest stumbling block on through here?
Great.
The trig guy down here. Yeah, so this is going to be, and I totally agree with you that we're all really good now at taking the derivatives. Now the question is, when we want to solve the derivative, setting the derivative equal to 0 and solving for x, that can be tricky. And in this case, this is what we have to do.
Thank you.
Okay, other questions on the practice problems? Okay. Then let's take a look at where we left off last time. So we started to talk about section 4.3, and the focus in section 4.3 is an analysis of local extrema and how derivatives give us information about an original function f. So 4.1, we were analyzing absolute extrema, finding absolute maximums and absolute minimums. That was 4.1. 4.3, we're talking about local extrema. So local extrema are local maximums and local minimums, meaning that we have a top of a hill or a bottom of a valley. It might be a cusp or it might be smooth. But it doesn't necessarily mean that it is the absolute highest place on the graph. It could just be kind of a small top of the hill and then there's a bigger mountain over to the right. But it still counts as something for us. Okay? And so we want to analyze how derivatives are going to give us information about local maximums and local minimums. And so I had drawn a picture, and we ended class last time by looking at this example. We had a picture of a function, and that function looked something like this. It had a sort of a parabola-shaped curve on the left-hand side, and then it reached a cusp right here at the y-axis. And then the curve dropped down and made a bowl that went a little bit below the x-axis. And then popped up here and created a hill, and then dropped down. Okay. So this was our original function, y equals f of x. And we labeled some of these points on here. We had a local minimum at A, B, and then a local maximum at C. And then we also had a local maximum at D. And so on this particular function, we have a derivative of 0 at A, B, and C, and a derivative that does not exist at x equals D. And so our critical numbers are x equals A, B, C, and D. Okay, so we have this function, and then we do the derivative. We drew the derivative. Y equals f prime of x. And the way that we drew this derivative, we looked at the flat places on our original function, and those became zeros on f prime. So x values of A, B, and C are all zeros on the f prime graph. The x value of D, which is x equals 0, our derivative does not exist. And so first our function f is decreasing, so our derivative is negative. And from A over to D, our original function f is increasing, and so f prime is positive. From D to B, our derivative is negative. Between B and C, f prime is positive, and the steepest point occurs about halfway between the x values of B and C, and so that's where we have a top of a hill on f prime. And then from C and on, our original function is decreasing, and so f prime is negative. Okay, so this is where we left off last time. We had drawn a picture of f prime. We were given f. We drew a picture of f prime. Are there any questions about these pictures? Jennifer?
From D, I understand that it's negative, but the slope is continuing negative, so I don't understand why we're going upward.
Wait, at which letter?
D.
At D, okay.
So the slope is negative.
Yes, so the slope up here is negative.
And so when we're negative on before A, it's, oh, okay, never mind. I see it now.
Okay, so what is it that you're seeing?
I'm seeing that I don't know, it's increasing, but I don't think it's supposed to be increasing.
So your f prime graph is increasing. That's what you're...
Well, that's why I'm confused, because this one I can see it going down, but this one to me seems like it's going upward. Like
so you're looking at f and seeing f going downhill,
yes.
and you're seeing f prime going uphill.
Yes.
And you're not liking that.
Yeah.
Okay. So hopefully, actually, after today, hopefully either I'm going to confuse you even more, or I'm going to help make it all clear.
Okay.
And so right now, rather than worrying about whether f prime is going uphill or downhill, for now just worry about the sign of f prime, knowing that f prime is below the x-axis.
Okay.
In terms of f prime increasing or decreasing, well, that depends on how steep the original function f is. And so here our slope on f is a very large negative number, whereas here the slope on f is still negative, but it's a small negative number.
Okay.
So our height down here is small negative versus large negative.
Okay.
All right, so I think what you would really like to do is to connect f double prime into all of this, and we're going to do that today. Okay, so other questions about the f and f prime? Okay, so some connections that hopefully we've been trying to make since the beginning of the semester. A major connection between these two pictures is this connection where when f is increasing, f prime is positive, meaning f prime is above the x-axis. And when f is decreasing, then f prime is negative, meaning f prime is below the x-axis. And so those two connections we've had for a little while. So I left you and I said, take a look at the local extrema on our original function. We have a local minimum at A and at B, and a local maximum at D and at C. Let's take a look at the local minimums. When f has a local minimum, so for example here at A, take a look at the f prime graph. Now, notice what's happening on the f prime graph. When our original function goes from going downhill to uphill, that means that our f prime is changing from below the x-axis to above the x-axis. And notice that that happens at A, when we had a local minimum, and also at B. As I read left to right, f prime is changing from negative to positive. So when f has a local minimum, f prime changes from negative to positive. All right, so let's take a look at our local maximum, and let's start with the local maximum that occurs at x equals c. At x equals c, our original function f is going uphill until it hits the top of the hill and then starts to go downhill. So our derivative f prime goes from being positive to being negative. And so when f has a local maximum, f prime changes from positive to negative. All right, now check out even this local maximum here where we had a cusp here at D. As I'm reading left to right on my derivative graph, positive derivative, positive derivative, positive derivative, oop, jump, negative derivative, negative derivative, negative. So we went from positive to negative. And in this case, it was a big jump, but we still went above the x-axis to below the x-axis. Okay? So that this statement is also true even at the funky non-differentiable point. All right, so these are pretty big connections. Are there any questions about those connections? Okay. All right, so places where f prime crosses the x-axis, not just touches it, but crosses it from one side of the x-axis to the other, are places where we have local extrema. Okay. So f prime is pretty cool because f prime tells us all the information about whether the original function is going uphill or going downhill. So when f prime is positive, our original function is going uphill. When f prime is negative, our original function is going downhill. And that's really just about it. That's about all that f prime can tell us. But if you remember, we went back and we looked at some derivatives and we said, well, what happens when you take the derivative of a derivative and the derivative of a derivative of a derivative of a derivative? So we had higher order derivatives. And so now the question becomes, why did we even bother talking about f double prime and f triple prime? And so our next question becomes, what does f double prime tell us about the original function Okay, so I'm going to pick a slightly less complicated function to look at for our first example. And so the example that we're going to look at is going to be a function that looks like this. This is y equals f of x. Okay, so here's our function y equals f of x. I'm going to draw a picture of y equals f prime directly below it. So y equals f prime, when I look at my original function f of x, I see that I have a slope of 0, I have a local minimum right at the bottom of the bowl here, so I'm going to label that point here and mark it down. F prime will be equal to 0 at the flat place on f. Now before that point, f is decreasing, so f prime will be below the x-axis. And after this point, f is increasing, so f prime will be above the x-axis. Okay, any questions about the picture of f prime?
You don't have to get into this, but those are straight lines. F prime is a straight line.
Yes.
Shouldn't there be a curve to it?
So it's not really clear based on the fact that I just have a picture here. I don't know whether, I mean, this could have a little bit of a curve to it. I mean, it could be, slightly bowed downward or bowed upward. And as long as my f prime function is going uphill, and as long as my f prime crosses the x-axis corresponding to where I have a local minimum up here, then that's a good enough estimate.
Okay, because in looking at these graphs, sometimes, when it's curving down to the local minimum or whatever,
Right.
It seems like there should be a curve, because it's changing a little bit.
So here, I mean, this could be a picture that might look more like that.
Right.
I'm ignoring some of the subtleties because I don't have more than just a rough sketch up here. Yeah. Okay. Good. Other questions? Okay. So take a look at our f prime graph. The fact that f prime is below the x-axis, before our critical number, I'll call our critical number here c. Before c, f prime is below the x-axis, and after c, f prime is above the x-axis. But if I just look at the graph of f prime, notice that f prime is increasing. Now, if I go back to my original function, and I draw some tangent lines of my original function, starting over here on the left side, I've got a tangent line which has a negative slope, pretty steeply negative. If I move over a little bit, and I draw another tangent line, that tangent line also has a negative slope. But it's not quite as badly negative as it was before. So I had a large negative number for my slope, and then a not so large negative number for my slope. So my slope is actually, in fact, increasing to a slope of 0. After this point, if I draw some tangent lines, I start to get positive slopes. And those slope values are getting larger and larger and larger as I move along my curve. So when I look at this function and I look at my tangent lines that I've drawn, the slopes of the tangent lines to our original function f are increasing. So our original function is decreasing until c and then increasing. But all along that curve, the slopes along that curve are increasing the entire time. So the height decreasing, then increasing, slopes increasing all the way across. All right, so that brings us to f double prime. So if I draw a picture of f double prime, looking at f double prime, well, I've got to look at f prime and say, okay, do I have any places on f prime where f prime's slope is 0? The answer is no. And in fact, I have a straight line, and so my slope of f prime is constant. It's a constant positive number. And so whatever that positive number is, I don't know what it is, but I can draw f double prime is going to be a horizontal line. Because whether I look at this point on f prime, or right at the x-intercept, or maybe someplace else, the slope of the straight line is exactly the same in all of those places. Okay, so f double prime will be positive and constant. Okay, so take a look at what we have drawn here. F prime is increasing. From left to right, f prime is going uphill. These slopes of the tangent lines on the original function, those slopes are increasing. F prime is the slope of the tangent, so it makes sense that both of those will be increasing together. When those things are happening, f double prime is positive. Okay, so when the slopes on the original function are increasing, it tells us that f double prime is positive. Now, this particular shape that we have here, something else you might notice about these tangent lines is every single one of these tangent lines was below the curve. Okay? None of them went on the inside, on the top half of this bowl. So everywhere along here, these tangent lines were below the curve. And a shape where your tangent lines are below the curve is a shape that's called concave up. When the tangent lines are all below the curve, we say the curve is concave up. And so when our original function has this shape that's called concave up, we know that f double prime is positive. And so a connection that we have is that f double prime being positive corresponds to f being concave up. And in fact, this is actually a triangle of connections. When f double prime is positive, that's because f prime was increasing. And so when f prime is increasing, its derivative, meaning f double prime, is positive. And when f double prime is positive, our original function f is concave up. And so these three things, these three properties, are all linked together. Okay, so let's take a look at, well, if we have concave up, there must be a shape that's called concave down. All right, so similarly, if I have y equals f of x, and my shape looks like an upside down bowl. In other words, on this first one, if it was raining and this was a rain catcher. The rain would actually fall in and get caught inside of our bowl. Whereas over here, well, there's not going to be much rain caught in here. It's all going to hit the top and just go off the side. Okay? This is an example of a curve which is concave down. And so if I want to be sure that this curve is concave down, I might draw a few tangent lines on it. And so when I draw a few tangent lines on f of x, every single one of those tangent lines lies above the curve that we're looking at. So a curve is concave down when all the tangent lines lie above the curve. All right, so when I draw when I draw f prime, y equals f prime of x, well, I look for the flat space on my original function f, and that will be the 0 on f prime. Up until that point, we'll call that value c. That's our critical number. Up until that point, f is an increasing function going uphill. So f prime will be positive. Now, while f prime is above the x-axis, take a look at what's happening to these slopes. We have a very large positive number, less large, even less large until we get to a slope of 0. And so our f prime graph, while positive, is decreasing because our slopes on the original function f are decreasing. And after c, the original function f is decreasing, and the slopes are also decreasing. So f prime is negative, and f prime is also decreasing. All right, so that tells us for y equals f double prime of x, since f prime is a decreasing function, its derivative will be negative. And so what that tells us is that when f is concave down, f prime is decreasing, and when f prime is decreasing, f double prime is negative. All right, so our first derivative tells us when the original function is going uphill or downhill. Our second derivative tells us a little bit more about the curves of the function. First derivative is pretty sort of robotic in the sense of uphill, downhill, that's all we get out of f prime. When f prime is positive, the original function is going uphill. When f prime is negative, the original function is going downhill. F double prime allows us to look a little more subtly at our function. When f double prime is negative, our curve, our original function, is concave down. When f double prime is positive, our original function is curved in a concave up manner. Okay. Any questions or comments about that? Will?
Yeah, so what is the point of knowing all this stuff if we could just like graph it and actually visually just see it?
So that's a really good question. And so, I mean, at this point, we're kind of cheating because we already have the original function f. But our goal in sort of understanding this is twofold. One is that understanding these connections between f prime, and f double prime allows us a deeper understanding of derivatives in general. But reality of it is when you go out into the workplace or wherever you're doing experiments, you're going to be measuring things such as the speed of the car rather than the distance that the car has moved, or the population growth rather than the actual population itself. So you're going to know information about f prime or information about f double prime, and you won't have an original function f to look at. So you're going to need to be able to use, you're going to want to be able to use information about f prime and information about f double prime to make predictions and statements about the original function f, even though you don't have a formula for that original function.
Gotcha, so it's setting us up for going back?
Yes, it's setting us up for, given this and this information, what can we say about this guy? Right now, we're saying, okay, given the original function, how does that connect to these other two? But eventually, this guy's going to be taken away from us.
Okay.
Other questions or comments? Okay. So before we wrap up for this hour, I want to give you one final definition. And I'll do the definition by first looking at a picture. So let's say I have a function, y equals f of x. And this function looks something like this. Okay, so we have a vertical asymptote, and then we have a few other positions on this graph. I don't quite want to make that last part flat up there. Okay. So some interesting information on here that I notice is that I have 2 points on here, and the first point that I'm marking here, I'm going to label as A, so the point itself is A comma f of A. And the second point that I'm going to label is over here on the right side, and it occurs at the steepest point along this increasing portion of our function. I'm going to call that point B. So this is the point B, comma, f of B. Now, take a look at our function that we have drawn here. Our function is increasing, 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 increasing all the way up to our vertical asymptote. But within there, take a look at the curvature of our function. From the left-hand side all the way up to A, my tangent lines are above the curve. And so our function is concave up, no, concave down on this first interval. And from A to our vertical asymptote, our function is concave up. And that point right there that splits the concave down and the concave up, that's a special point. That's called a point of inflection. So a point of inflection is a point on a curve where the curve changes from concave up to concave down, or vice versa. In other words, a point of inflection is a point where the curve changes concavity. All right, so point A is a point, A comma f of A is a point of inflection. And so I can write that as a POI if I want to, point of inflection, or inflection point, IP. And then over here at the point B, from our vertical asymptote over to x equal to b, our curve is concave up. And then right at B, we switch to concave down. So on our picture here, our 2 points of inflection are A comma f of A and B comma f of B. Just a second, let me write that down. So points of inflection are A comma f of A and B comma f of A. Okay, look.
So if you had this coming from the other direction, would that asymptote, like if the next one was concave down, would that asymptote also count as a point of inflection, or no?
Well, so what's going to happen is, so if, let's say that I had a picture that looked, say a vertical asymptote here, and our curve maybe looked like this, and then over here we had a curve like that.
Yeah.
So here at this x value, let's call that A. At that x value, we've changed concavity, but unfortunately, x equals A is not part of our domain of this function. So it's a place where our concavity changes, but it's not technically a point on the curve, so I don't think we can call it points of inflection. Yeah, but we do change concavity at x equals A. We just don't have an inflection point. Good question. Okay. So are there any other questions about our definition of inflection point or about f double prime? All right. In that case, let's stop here. This is a lot of information to absorb. Stop here, take a 10-minute break.